Hello friends, today we are going to deal with the law of conservation of momentum and its application, especially from the point of view of collision. I am going to refer to the famous book of Halliday, Rusnick and Walker, that is Fundamentals of Physics. So let us begin our discussion. Linear momentum we define as mass into velocity, and we denote that with letter capital P bar. V being vector, P is also a vector. M is mass of the object measured in kg and velocity measured in meter per second. So SI unit of linear momentum is kg meter per second. The second law of Newton, rather Newton's second law of motion, F is equal to dt of P, that is rate of change of momentum, and we replace momentum P by m into V, and we can treat m to be constant multiplied by dv by dt, that is rate of change of velocity, which is in fact acceleration. So F is equal to ma is a derived version of Newton's second law, and the unit for measuring force in MKS system is kg meter per second square. Now, when the force, external force is absent, that is F equal to 0, in that case F is replaced by dp by dt, and this is turning to be 0, it means that momentum must be constant. Suppose that the external force and thus the net impulse acting on a system of particles is 0. The system is isolated and that no particle live or enter the system being closed, and we can represent that by equation P equal to constant. Now, the law of conservation of momentum in case of collision, we state a, a definition before collision and a definition after collision as summation of all momentum of particles. Sum of momentum of all particles before collision is essentially equal to summation of momentum of all particles after collision. So here n and m being different means that the conservation of number of particles is not taken care of. Couple of particles can merge or split, that is not an issue, but vector sum of all momentum before collision is equal to vector sum of all momentum after collision, I mean for all particles. Now, this is only true for closed system, that is under a rider when force is absent. So I redefine the principle of conservation of linear momentum as when the force is absent, when the external force is absent, the vector sum of momentum of all particles before collision is equal to vector sum of momentum of all particles after collision. And thus we rewrite that as total linear momentum at some initial point, that is before collision, is equal to total linear momentum at some later time after collision, Tf. They are one and the same. The linear momentum of a system of particles is conserved in case of collisions if there is no external force acting on it. So, summation of momentum before collision is equal to summation of momentum after collision. So P1 bar, P2 bar, P3 bar and so on up to Pn bar is momentum before collision, then it is exactly equal to P1 bar dash plus P2 bar dash and so on up to Pm bar dash, that is after collision. So M1 V1I plus M2 V2I is equal to M1 V1F plus M2 V2F. So I stands for initial, that is before collision, and F stands for final, that is after collision. So collisions are categorized into two sections. One is elastic and another one is inelastic. In case of all collisions, the total linear momentum before collision is equal to total linear momentum after collision. So conservation of linear momentum is applied to all collisions. Either it is elastic or inelastic. But what is the speciality of elastic? The total kinetic energy is conserved in case of elastic. That is, total kinetic energy before collision is equal to total kinetic energy after collision. So in case of elastic collisions, kinetic energy is conserved. The total linear momentum of a system cannot change because there is no net external force to change it. This is a very powerful rule because it can always allow us to determine the results of collision without knowing much details of collision, such as how much damage is done. We shall also be interested in the total kinetic energy of the system of two colliding bodies. If the total happens to be unchanged by the collision, then the kinetic energy of the system is also conserved. It is the same before and after collision. Such collision is called elastic collision. In every collisions of common bodies such as two cars or a ball and a bat, some energy is always transferred from kinetic energy to other forms of energy such as thermal energy or energy of sound. Thus, the kinetic energy of the system cannot be conserved. Such collision is called as inelastic collision. Howsoever, in certain situations, we can approximate a collision of a common bodies as elastic. Suppose that you drop a super ball on the hard floor. If the collision between the ball and the floor, that is earth, were elastic, then the ball would lose no kinetic energy because of its collision and would rebound to its original height. However, the actual rebound height is somewhat short, showing that at least some kinetic energy is lost in the collision, and thus the collision is somewhat inelastic. Still, we might choose to neglect some small loss of kinetic energy to approximate the collision as elastic. The inelastic collision of two bodies always involves a loss in the kinetic energy of the system. The greatest loss occurs if the bodies stick together, in which the collision is called completely inelastic. The collision of a baseball and a bat is inelastic. However, the collision of a wet putty ball and a bat will be completely inelastic because the putty sticks to the bat. Now for the case of elastic collisions, we shall consider a couple of equations. The first equation is for the case of collision Does not matter whether it is elastic or inelastic. That is m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2, where I am considering two masses m1 and m2 with initial velocities u1 and u2, and v1 and v2 involved are the final velocities. In case of elastic collision, the kinetic energy is conserved. So I am bound to find 1 by 2 m1 u1 square plus 1 by 2 m2 u2 square will be the total kinetic energy before collision. That should be equal to total kinetic energy after collision. That is 1 by 2 m1 v1 square plus 1 by 2 m2 v2 square. Now let us deal with an example wherein we have 2 kg mass moving to the right with velocity 5 meter per seconds. It collides head-on to the stationary 3 kg mass. Stationary means U2 is 0. Assuming the collision is perfectly elastic, determine final velocities of both the masses. So obviously m1 2 kg, v1 5 meter per second plus 3 kg stationary velocity 0, u2 is 0, that is equal to 2 times, that is I am talking about m1 v1, 2 times v1 plus 3 times v2, where v1 and v2 are unknown. So a single equation can never offer us a value of these two velocities. So conservation of kinetic energy we are considering because the collision is referred as perfectly elastic. So 1 by 2 I am eliminating in the whole equation. I am just substituting values. m1 is 2, u1 is 5, m2 is 3, u2 is 0, 2 times, m1 is 2 and v1f square plus 3 times v2f square. So one has to solve this pair of equations. This is a simplified version of the first equation, and simplified version of second equation can be solved together for v1 and v2 minus 1 meter per second, 4 meter per second. I would like to request students to pause this video and really pick up a piece of paper and just work out the answers, which are minus 1 and 4. You'll find some trouble which I'm going to ease out in the next processing of equations. In the earlier example, we have faced a trouble because first equation of conservation of linear momentum was pertaining to velocity, and second equation pertaining to kinetic energy was pertaining to velocity square. So that causes a bit troublesome situation in evaluating values of velocity. Here we shall try to eliminate that. Here we have the same equation of conservation of momentum, and we are collecting terms pertaining to m1 on left hand side and m2 on right hand side. So here we obtained the equation that I'm going to call A. For equation of conservation of kinetic energy, again I am doing the same thing, where m1 related terms are clubbed together on left hand side, while m2 related terms are clubbed into right hand side. So x square minus y square, we can write x minus y into x plus y. Exploring that formula, we have second equation that I'm going to call as equation B, and A upon B I'm going to refer, wherein you can eliminate some common part in the numerator and denominator and conclude u1 plus v1 is equal to u2 plus v2, and u1 minus u2 is equal to minus times v1 minus v2. So difference of velocities before collision is equal to minus times difference of velocities after collision. Direction is opposite. Speed of approach is equal to minus times speed of receding away or going apart. So u1 minus u2 is equal to v1 minus v2 in simplified version. And finally, you can write velocity v2 in terms of v1 using this, and it can be substituted in the last equation A that we are considering as conservation of linear momentum. So reconsider our linear momentum conservation equation, and here V2 term we are going to write in terms of V1, and the last formula we are exploring V2 is equal to U1 minus U2 plus V1. Substituting it here, and we can isolate V1 terms on left hand side, and you can observe that V1 into M1 plus M2 is equal to M1 minus M2 U1 plus twice M2 U2, and in toto we can write V1 is equal to M1 minus M2 upon M1 plus M2 times U1 plus twice M2 upon M1 plus M2 U2. Similarly, we can obtain V2 velocity. And now we can explore these formulas for V1 and V2. Here we shall reattempt the problem where M1 is 2 kg, U1 is 5 meter per second, M2 is 5 kg, U2 is 0, and we have to assume the collision to be perfectly elastic to find V1 and V2. So just now we have derived this formula wherein we are going to substitute M1 is equal to 2, M2 is equal to 3, and U1 is equal to 5, M2 is equal to 3, and U2 is equal to 0. This leads to minus 1, and second formula also we can explore to obtain V2 is equal to 4. So by a little algebraic processing offers us a better version of formulas for V1 and V2, which students can explore in the examination for solving the numericals.